Imagine a world where the surface is frozen solid, temperatures are brutally cold, and sunlight is so weak that the landscape seems almost completely lifeless. Now imagine that beneath that frozen surface, there may be a global ocean of salty liquid water, and that ocean is spraying samples of itself into space. That world is Enceladus, one of Saturn's smallest major moons. It's only about 500 kilometers across, yet it has become one of the most intriguing places in the entire solar system. Because something is happening beneath the ice. Enceladus has enormous fractures near its south pole. Through those fractures, jets of water vapor and icy particles erupt into space. And this changes everything. Scientists don't have to drill through kilometers of ice just to get a sample of the hidden ocean. The ocean is, in a sense, coming to them. NASA's Cassini spacecraft actually flew through these plumes and analyzed their contents before the mission ended in 2017. And what Cassini found was astonishing. Water, salts, organic compounds, molecular hydrogen, phosphorus, and evidence pointing toward hydrothermal activity at the ocean floor. But here's the mystery. All of those discoveries tell us that Enceladus could be habitable. They do not tell us that it is inhabited. So what exactly is happening beneath that ice? And if life ever arose there, could we actually detect it? If that possibility already has your attention, hit like, because the deeper scientists looked, the stranger Enceladus became. For a long time, Enceladus didn't look like a particularly promising place to search for life. Before Cassini reached Saturn, scientists knew it was small, icy, and incredibly bright. In fact, Enceladus is the most reflective body in the solar system. Its surface reflects so much sunlight that it looks almost brilliant white. Voyager spacecraft images in the 1980s gave scientists their first detailed look, revealing smooth regions with surprisingly few impact craters. That suggested something important. At least parts of Enceladus had been resurfaced relatively recently, but nobody initially had a complete picture of what was happening underneath. Then Cassini arrived at Saturn in 2004, and Enceladus began breaking the old model. During observations in 2005, Cassini detected a cloud of water vapor near the South Pole and discovered an unusually young, active landscape cut by enormous fractures. These fractures became known as the tiger stripes. 4 major fractures stretch for roughly 135 kilometers across the South Polar region. And they weren't just scars in the ice. They were active vents. Material was escaping from inside the moon. The discovery completely changed the scientific importance of Enceladus. A tiny frozen moon had suddenly become an active world. But scientists still faced a huge question. Was there actually a large body of liquid water beneath the surface, or were these jets coming from a much smaller underground reservoir? That distinction matters enormously. A local pocket of water is interesting. A global ocean is something else entirely. Then came another clue. Cassini's gravity measurements suggested there was more mass beneath the South Polar region than the surface alone could explain. And researchers began piecing together evidence that Enceladus wasn't simply a frozen rock with a little water trapped underneath. Something much bigger was happening. If this were simply an ordinary icy moon, the story should have ended there. It didn't. The crack in the old model came from something you might not expect to be useful in finding an ocean: a wobble. As Enceladus travels around Saturn, it rotates. Cassini scientists spent more than 7 years tracking the positions of surface features with extraordinary precision. They discovered that the moon's icy outer shell isn't locked rigidly to its rocky interior. The crust appears to move independently, and that subtle motion is called libration. The simplest explanation? There has to be liquid separating the ice shell from the interior. In 2015, researchers published evidence that Enceladus possesses a global subsurface ocean rather than merely a small regional sea. Think about what that means. A moon only around 500 kilometers wide has a shell of ice surrounding a planet-sized geological mystery. Not a planet-sized ocean in volume, but a global body of liquid water extending around the moon. And above it is an ice shell. Below it is a rocky interior. Somewhere down there, water is interacting with rock. And at the South Pole, material from that environment is escaping through fractures. Suddenly, Enceladus wasn't just an icy moon. It became an ocean world. But there was another problem. Where would the energy come from? Liquid water alone doesn't guarantee life. Earth has plenty of frozen water. Mars has water ice. Some asteroids contain water-bearing minerals. But life needs more than water. It needs chemistry and an energy source. So scientists started asking a much more interesting question. Could Enceladus's hidden ocean actually have the ingredients needed to support biology? And if so, where would that energy come from? The answer began appearing in the chemistry of the plumes. And that's when this frozen world became much harder to dismiss. Imagine being a scientist and discovering that a distant moon is throwing material from its hidden interior directly into space. You don't need to land. You don't need to melt the ice. You don't even necessarily need to reach the ocean. You can sample what the moon is already ejecting. That was the extraordinary opportunity Cassini provided. During its encounters with Enceladus, the spacecraft passed through the plume and analyzed gases and icy grains. The results revealed a chemically complex environment. Cassini detected water vapor, carbon dioxide, methane, ammonia, and other compounds. The spacecraft also detected molecular hydrogen. And hydrogen was especially interesting, because on Earth, hydrogen can provide chemical energy for certain microorganisms. That doesn't mean Cassini found microbes. It didn't. But it suggested that Enceladus's ocean may contain a source of chemical energy that life could potentially exploit. Then came another clue. Cassini detected tiny silica particles. Scientists concluded that these particles were consistent with formation in hot water interacting with rock before entering the colder ocean. That is one of the reasons researchers have inferred the possibility of hydrothermal activity on the seafloor. So picture the environment. An ocean beneath kilometers of ice. A rocky interior. Water circulating through or interacting with rock. Heat moving through the system. Chemicals being transported upward. And eventually, some of that material reaching space. If you're thinking, that sounds strangely familiar, you're onto something. Because on Earth, hydrothermal vents support ecosystems that don't depend directly on sunlight. Could something analogous happen on Enceladus? That's one of the biggest questions in planetary science. But the next discovery pushed the question even further. Here's where the science gets really interesting. On Earth, the deep ocean contains ecosystems built around chemistry rather than sunlight. At hydrothermal vents, seawater interacts with hot rock, producing chemically rich environments. Microorganisms can use chemical reactions to obtain energy, and larger organisms can build entire ecosystems around them. Enceladus doesn't need to look exactly like Earth for chemistry to matter. Scientists are interested in whether its ocean contains the ingredients and energy gradients that could make biology possible. Cassini's detection of molecular hydrogen became especially important. The spacecraft's measurements indicated that the plume's gas was overwhelmingly water vapor, with roughly 1% molecular hydrogen and smaller amounts of other gases including carbon dioxide, methane, and ammonia. Why is hydrogen important? Because one possible reaction involves hydrogen combining with carbon dioxide, releasing energy. On Earth, some microorganisms use reactions like this. But there's a critical scientific distinction here. A chemical energy source is not evidence of life. It is evidence of a potentially habitable environment. That distinction has to remain clear. Scientists aren't saying, "We found aliens." They're saying something much more scientifically useful. We found an environment where some of the requirements for life as we know it may exist. And then came phosphorus. In 2023, researchers analyzing Cassini data reported the detection of phosphorus in salt-rich ice grains from Enceladus's plume. Phosphorus matters because it's part of biological molecules, including the phosphate backbone of DNA and RNA, and energy-related molecules such as ATP on Earth. The measurements suggested that phosphorus could be relatively abundant in the ocean. Suddenly, another piece of the habitability puzzle appeared. Water? Yes. Organic chemistry? Yes. Chemical energy? Evidence suggests yes. Phosphorus? Detected in plume material. Hydrothermal activity? Strong evidence points in that direction. And that's a remarkable collection of ingredients for such a small, frozen moon. But then new data changed the story again. because scientists went back into the Cassini archive, and they found chemistry that had been waiting for years to be understood. This is the twist. Cassini stopped operating in 2017, but the science didn't stop. Researchers have continued analyzing measurements collected during the mission. In 2025, NASA reported a new analysis of ice grains captured by Cassini during a close flyby through Enceladus's plume. The researchers identified previously undetected organic compounds. And importantly, these weren't simply old particles sitting on the moon's surface. The analysis focused on fresh plume particles originating from the subsurface environment. The spacecraft had flown through the plume only about 21 kilometers above Enceladus's surface during the relevant sampling. That matters because it gives scientists another window into the ocean chemistry. The discovery doesn't prove biology. Organic molecules can form through non-biological chemistry. But it demonstrates that the hidden ocean environment is chemically richer than some earlier analyses revealed. And scientists had already found another fascinating molecule. In 2023, a study of Cassini data provided strong confirmation of hydrogen cyanide in the plume. That molecule is extremely important to origin of life chemistry because it can participate in pathways leading toward biologically relevant compounds. Again, no aliens, no fossil microbes, no biological cells, just chemistry. But chemistry that makes the scientific question much more interesting. Because if complex organic chemistry can occur inside an ocean hidden beneath an ice shell without sunlight reaching the ocean, then Earth may not be the only place where potentially life-supporting chemistry can happen. And that changes the search strategy. For decades, the search for life beyond Earth often focused on planets around stars, places with sunlight, temperatures that might allow liquid water at the surface. But Enceladus forces us to think differently. A world doesn't necessarily need a warm surface to have a potentially habitable environment. It might only need liquid water, chemistry and energy hidden underneath ice. And suddenly, the solar system may contain far more interesting worlds than we once imagined. If you had to choose, would you rather explore a planet with a barren surface or an icy moon whose ocean is actively sending samples into space? So how does Enceladus keep an ocean liquid when it's so far from the sun? The answer is gravity. More specifically, tidal forces. Enceladus orbits Saturn, while Saturn's enormous gravitational field constantly pulls on the moon. But Enceladus's orbit isn't perfectly circular. Its interactions with Saturn and other moons help maintain orbital eccentricity, producing changing gravitational stresses. Those stresses deform Enceladus. The moon is repeatedly squeezed and stretched. That mechanical deformation generates heat inside the interior. It's called tidal heating. And this is one of the reasons Enceladus can maintain internal activity despite being so far from the sun. The result is a fascinating energy system. At the surface, temperatures can plunge to extremely low levels. But deep inside, tidal energy can help maintain liquid water and geological activity. The ice shell acts as an insulating blanket. The ocean sits between that shell and the rocky interior. And at the bottom, water may interact with heated rock. Scientists have evidence consistent with hydrothermal activity, including the detection of silica particles and hydrogen in the plume. Imagine the scale. You're standing, or rather, imagining standing, on an icy world under a black sky. Below your feet is kilometers of frozen material. Far beneath that is a global ocean. And beneath the ocean is rock. Somewhere in that hidden environment, water and rock may be exchanging heat and chemicals. Above you, fractures in the ice release material from that environment into space. It's almost as if Enceladus has accidentally built a natural sampling system. And that's why the moon is so valuable scientifically. We don't have to reach the ocean first to start asking questions about it. Cassini effectively sampled the ocean environment remotely. But there's a limit. Cassini wasn't designed specifically as a life detection mission. It found habitability clues. It didn't settle the question of whether anything is alive. To answer that, scientists need much better instruments. And that's where the future becomes fascinating. If this story has changed how you think about what a habitable world looks like, subscribe for more real space discoveries. Because the next mission could bring us much closer to an answer. The stakes are much bigger than one moon. If Enceladus is inhabited, or if it once hosted life, that would completely change our understanding of where life can exist. Think about what Earth tells us. Life here is incredibly adaptable. It survives in boiling environments, acidic waters, deep underground, and places where sunlight barely reaches. But Earth gives us only one example of life. We don't yet know whether biology is common or extraordinarily rare. That's why ocean worlds are so important. There may be liquid water hidden beneath the ice of several worlds in our solar system. Jupiter's Europa is a major example. Titan, Saturn's largest moon, is also believed to have a subsurface ocean. But Enceladus has an extraordinary advantage. Its ocean is not completely sealed away. Material from inside is naturally being expelled into space. That's a huge gift for planetary scientists. Instead of drilling through an enormous ice shell, a spacecraft can potentially fly through the plume and collect material. NASA has already demonstrated the basic concept with Cassini, and future missions could do it far more deliberately. Now, consider what a positive life detection would mean. It wouldn't simply add another interesting organism to a biology textbook. It would tell us that life emerged independently somewhere other than Earth, or at least that biology exists somewhere else. That would be one of the most profound discoveries in human history. But even a negative result would be scientifically valuable. Suppose a future mission samples Enceladus repeatedly and finds an incredibly rich chemical environment, but no convincing evidence of life. That would tell us something important about the relationship between chemistry and biology. It could help answer a much deeper question. Is life an almost inevitable outcome when water, energy, and chemistry come together? Or is there another missing ingredient? And that's the real scientific tension. We're not simply looking for aliens. We're trying to understand how difficult, or how easy, it is for life to begin. If life exists on Enceladus, would you expect it to resemble anything on Earth? Or could biology in a completely different environment surprise us? So what happens next? Scientists already have concepts for missions designed specifically around Enceladus's remarkable accessibility. One of the most ambitious is the Enceladus Orbolander concept developed for NASA studies. The basic idea is extraordinary. A spacecraft would orbit Enceladus, study its plume, then land on the surface and analyze material there. The mission concept is designed specifically around searching for signs of life. NASA's current concept documentation describes instruments capable of analyzing plume material and surface samples, including organic compounds and potential biosignatures. But there's an important caveat. The Orbolander is a mission concept, not an approved mission currently on its way to Enceladus. Its science concept has been studied as part of NASA's long-term planetary exploration planning. ESA has also identified an Enceladus mission as a long-term goal in its Voyage 2050 planning, specifically to search for life in the Moon's subsurface ocean. And researchers are already thinking about increasingly creative ways to sample the plumes. A 2025 NASA Innovative Advanced Concept Study proposed LEAP, a concept involving a jumping robot that could move across Enceladus's low-gravity surface and potentially collect material from multiple jets. These aren't promises that robots are about to land there. They're examples of how scientists are turning Enceladus's natural plumes into a strategic advantage. Because the question isn't simply, is there water? We already have strong evidence that there is. The question is, what is happening inside that water? Is the chemistry purely geological? Did complex organic chemistry develop without biology? Or is something alive hiding beneath the ice? And perhaps the most exciting question of all, could a future spacecraft actually answer that? Enceladus is a strange reminder that appearances can be deceptive. From a distance, it's just a small white moon orbiting Saturn. Cold, dark, frozen, but underneath that surface, there's a global ocean. That ocean contains salts and organic compounds. Its chemistry includes phosphorus. Its plume contains molecular hydrogen. Cassini found evidence consistent with hydrothermal activity, and newer analyses of Cassini data continue to reveal previously undetected organic compounds. None of this proves that Enceladus is alive, and that's important. Science hasn't found an alien organism there. What scientists have found is something arguably more frustrating: and more exciting. A place where the conditions for life as we understand them may exist, while the final answer remains hidden. And that mystery is why Enceladus matters. Because if life is discovered there, humanity will have to confront a staggering possibility. Life may not be a one-world phenomenon. And if life isn't found, we'll still learn something fundamental about how planets and moons create, and fail to create, the chemistry needed for biology. Either way, the frozen surface is only the beginning. The real story is underneath. Somewhere below that ice, an ocean is moving through darkness. And for now, we can only study the tiny pieces that escape into space. But the next generation of missions may be able to get much closer. Maybe close enough to answer the question we've been building toward this entire time. Is Enceladus simply a chemically rich ocean world, or is something alive inside it? If this changed the way you see the solar system, hit like. Drop your biggest question about Enceladus in the comments. And subscribe to the Coded Tales for more stories about the worlds that could change our understanding of the universe. Because this story isn't finished. The ocean is still there. The plumes are still revealing clues. And somewhere beneath that frozen crust, the answer is waiting.